The excitement, I have lost my sheet. So I will have to make something online. I'm sorry. But Professor Weinberg, he comes from University of Texas in Austin, and I would say he's the greatest theoretical physicist of our time. There's nobody like him. He's really very unique. Now, if you don't believe me, look at his homepage, or look at Wikipedia, or consult the web pages of Nobel Foundation, Nobel Prizes. And so we are really very, very happy that he could come here to deliver a talk in honor of Gunnar Källén. Gunnar Källén was a professor of theoretical physics here. He got a personal professorship in 1958. He came then directly from CERN Theory Division. He was the second person employed by CERN Theory Division. The CERN Theory Division was in those days in Copenhagen at the Institute of Theoretical Physics. Unfortunately, he was here only for 10 years and then he died in a plane crash. He was extremely talented. I was very sad that he did not really live to see the blossoming of a standard model and all these things which we got afterwards, the field theory which came into action here. Actually, there's a connection between Professor Weinberg and Källén. I'm not going to tell you so much about it because I think Steve is going to tell you. But I can only quote, if you allow me, from your very first published paper, according to the Web of Knowledge. I can quote. You wrote a paper, your very first published paper, according to Web of Knowledge. And if you go to the Acknowledgments, what does it say? The author is the gentleman sitting there. What does he say? The author wishes to express his gratitude to Dr. Gunnar Källén for suggesting this problem. See? This problem. Suggesting this problem. And for many valuable discussions. Then you go on, because you're very polite. He also wishes to thank Professor Niels Bohr for the hospitality of the Institute for Theoretical Physics of Copenhagen, where this work was begun. I think there's nobody in the world who could really explain to us what Gunnar Källén meant to physics, what he had done. Nobody at all of your class. So we are really looking enormously forward to your talk about Professor Gunnar Källén. Please.
Thank you. Thank you, Cecilia. I'm glad you lost the written introduction. It couldn't possibly have been as nice as this one was. We're here on the 83rd birthday of Gunnar Källén. I'm delighted to have this time and to have this opportunity in helping to commemorate his birth. He died tragically just a few months more than 40 years ago. I feel this way because I owe so much to Gunnar Källén. I arrived in Copenhagen in the summer of 1954, having just completed my undergraduate studies at Cornell. And as Cecilia said, Källén was then at Copenhagen at the Theoretical Study Division of CERN, which had not yet moved to Geneva. I was advised to go to Copenhagen by Richard Dalitz, who was visiting Cornell, in part because of the presence of CERN in Copenhagen. But the real reason that I went to Copenhagen is that my wife and I were just married, and we both wanted to have a romantic year abroad, which we did. I arrived with a bag of books, which I intended to study. I wasn't a complete wastrel, but I really had no idea of beginning to do research, because I was under a terrible misapprehension, which many students are, that in order to do research in every field, you first have to learn all about everything that's been done in that field. And it's not true, but I thought it was true, and I knew for sure what was true, that I didn't know everything about anything. And so I would just sit and, I planned to just sit and go through these books. It wasn't long before the physicists at the Niels Bohr Institute told me that, no, everyone at the Bohr Institute is doing research. You have to find something to do. So being obedient, I went around, I had no idea of my own. I asked for help. The first help I got was actually from David Frisch, who some of you may know, may remember. He was a very good nuclear physicist at MIT who was visiting Copenhagen that year. He suggested a problem on alpha decay, nuclear alpha decay, but I couldn't make anything out of it, and nothing came of that. And then sometime later that year, either late in 1954 or early in 1955, I heard about a young theoretical physicist named Chilene, who was doing very interesting things in the quantum theory of fields. And the quantum theory of fields, well, all I knew about it was that it was a very sexy subject. So I went to Chilene, I knocked on his door, and I asked for a topic to do research on. And as it happened, Chilene had a research topic that he wanted someone to work on. It had to do with a very interesting model of elementary, not a serious model, but what we call a toy model of elementary particles, proposed a year earlier by a physicist at Columbia named T.D. Lee. This model had the virtue of being exactly soluble. That was the interesting thing about it. It had some peculiarities, some things that seemed unphysical about it, which I'll come back to later in my talk. That didn't seem to bother Lee, and Lee did some calculations which seemed to work out and give reasonable results. As I said, you could solve the model exactly, so you get precise results in the model. Chilene and Pauli smelled a rat and studied the model and found that indeed it violated the principle of unitarity, which is a fancy way of saying that when you studied a collision processes and evaluated the probabilities of various things happening in the collision, the probabilities didn't add up to 100%, which must be wrong. Chilene and Pauli published a paper reaching this result, and then Chilene suggested that I look further at the Lee model to see if anything else was wrong with it. Well, with a great deal of help from Chilene, I was able to show that in addition to probabilities not adding up to 100%, this was a model in which when you calculated the energies of certain states, you got complex values, that is, values which are not ordinary real numbers. I finished that work on a Danish freighter of Det Forenede Dampskibsselskab, and that's about all the Danish I know. On going back to the United States at the end of the year in Copenhagen, and very soon after I started graduate work in Princeton, I had published my first paper, the paper that Cecilia was kind enough to mention, called NV Potential in the Lee Model. This was a very unimportant paper. I recently checked. I normally don't check this sort of thing, but for the purpose of this talk, I did check. And in the 53 years since this paper was published, it has been cited 9 times. You got how many? 16. I got 9. Well, that destroys my joke, because I was going to say that when this talk is published, it will bring it up to 2 digits. But the paper, although very unimportant to the world of physics, was important to me because the experience of doing this, even though I had gotten a great deal of help to Chilene, made me feel that I was a physicist and not a student, and so I was able to complete my graduate work in Princeton in a very short time. Chilene's kindness to me and my wife went beyond his help with this research, great as that was. He had my wife and me to dinner at his house, and at that dinner, I went to the bathroom and I learned something about Chilene that I don't think anyone knows, and that is that he had hand towels embroidered with the Dirac equation. I mentioned this to Mrs. Chilene, and she said they were a present from Pauli. And Chilene also did me the great favor of introducing me to Pauli, so I'm so proud to say I met him, but I didn't get any towels. But although this experience was a valuable one, there was something odd about it, which I felt at the time but didn't really understand until much later. The Lie model was not intended to be a realistic model of elementary particles. The only virtue of the model was that it was exactly soluble. It wasn't a relativistic theory. And also, Lie at that time was not well known. His great work with Yang on parity violation was a few years in the future. So why did Chilene bother spending so much effort in shooting this model down? He not only worked on himself, he enlisted the help of his friend Pauli, and then after Pauli and Chilene had killed off the model by showing that it didn't satisfy unitarity, he enlisted me to continue beating the dead horse. I think the explanation as I understood it later was because this had to do with a controversy in which Chilene was playing an important part at the time. And I had gotten into this controversy without even really understanding what the controversy was. It had to do with the significance of infinities in quantum field theories. In any quantum field theory, when you have a physical process, you have to sum over the intermediate states between the initial and the final states of, say, a collision process. And in that intermediate states, the particles can share the energy in an infinite variety of ways. You have to integrate over the energies of the individual particles. And those integrals frequently diverge so that you get infinity for when you calculate a probability. Even worse than getting probabilities that don't add up to 100%. They sometimes come out infinite. Or energy shifts can turn out to be infinite. The first person who suspected the presence of infinities in quantum field theories were actually Heisenberg and Pauli in their 1929 papers, where they first presented the formalism of quantum field theory. And then in actual calculations, they were discovered here in Sweden by Ivar Waller in calculating the energy shift of the energy of a free particle due to emitting and then reabsorbing photons. The integral over the energy of the photon in the intermediate state, what we call a virtual photon, diverged logarithmically. And Oppenheimer did a similar calculation at about the same time for electrons bound in orbits in atoms, and again found logarithmic divergences. This discovery of infinities by Waller and Oppenheimer in 1930 led to a mood of pessimism about the future of quantum field theories, which persisted throughout the 1930s. And some physicists, including Oppenheimer, felt that there was something wrong with quantum field theory that meant you couldn't trust any applications of quantum field theory at energies above about 100 MeV. excuse me. After the war, new calculational techniques were developed, by Feynman and Schwinger and Tomonaga, and they were techniques that allowed for the preservation of relativistic invariance, the principles of special relativity, at every stage in the calculation. And using these new techniques, it was possible to implement an older idea due to Kramers and Weisskopf that the infinities perhaps could be absorbed into a redefinition of the constants of the theory. That is, when you write down a physical theory like quantum electrodynamics, you write down field equations in which there are certain constants, like the charge of the electron and the mass of the electron. Those aren't the quantities that are actually calculated because the electron is surrounded with a cloud of photons that it's continually emitting and reabsorbing. The thing that has to be finite is the physical mass and the physical charge of the electron, but the bare mass and bare charge can be infinite, and in fact they can be given infinite values which just cancel the infinities that you get when you calculate integrals over the energies of intermediate states. This is called a renormalization of the constants. And Freeman Dyson was able to show that this would work in all orders of perturbation theory in quantum electrodynamics and in a certain limited class of other theories. There were a few loose ends in Dyson's proof which were later sewed up by Abdus-Salam and myself. The theories in which this works, that is, in which the infinities can be cancelled by infinities in the bare parameters appearing in the theory. In other words, they can be absorbed into a renormalization of the constants of the theories. These theories are called renormalizable theories, and they can be recognized by the fact that the constants appearing in the equations are in natural units where we choose the units of length and time so that Planck's constant and the speed of light are 1. In natural units, the constants are either dimensionless, like the charge of the electron, e squared over 4 pi, and those units is 1 over 137, or have units that are positive powers of energy, like masses. A mass has the same units as energy when the speed of light is 1. Theories with constants that are negative powers of energy are regarded as non-renormalizable, and this was thought would not work in that case. But quantum electrodynamics, since the only constants in quantum electrodynamics are the charge of the electron, which has no units, and the mass of the electron, which is the same units as energy, that's a renormalizable theory. And this led to a new wave of enthusiasm for quantum electrodynamics and quantum field theory following this work at the end of the 1940s. And most theorists then went on using quantum field theory without worrying about the infinities at all. They just took it in their stride. Some indeed even thought that the fact that they were seeing infinities at all in the bare mass and the bare charge of the electron in quantum electrodynamics was a symptom of the fact that they were doing perturbation theory. Perturbation theory means you're expanding physical quantities as a power series in powers of the charge of the electron. And we don't know whether that series converges. Many people think it doesn't converge, almost certainly doesn't converge. It's probably an asymptotic series, which gives good results because e squared over 4 pi is as small as 1 over 137. Some theorists thought when we learned to do without perturbation theory, we would see that the infinities all went away. There were two leading theorists who thought just the opposite, who thought that in fact, when you really understood the theory beyond the limits of perturbation theory, you would see that the infinities were symptoms of something really wrong with the theory that limited its application and prevented it from being applied at energies as high as, well, some very high energy, but limited the energies at which could be applied. Those theorists were Lev Landau and Gunnar Källén. Chilene set himself the task of trying to study these infinities without the use of perturbation theory, without any expansion in powers of the charge of the electron, to see whether or not the theory really broke down. The first task, which he addressed in a paper in 1952, was to define what you mean by the bare charge of the electron and so on, without the use of perturbation theory, because until then it had only been understood perturbatively. To explain what Chilene did, just to save a lot of writing, I'll take a simpler example than quantum electrodynamics, which was studied 2 years later by Harry Lehmann, where you, instead of an electromagnetic field, which has a vector nature, you just take a scalar field. Lehmann gave a, well, you really should think of Chilene because he did this first, but he did it in the case of electrodynamics. So I'll say Chilene, although it was really Lehmann who worked on it was really Lehmann who worked on the scalar field theory. Chilene was studying a quantity called the propagator, for which I'll use this symbol. By the way, this is a terrific new technology which may replace PowerPoint. You write on the with chalk, you write on the blackboard, and then you can make corrections in real time. It's really in terms of perturbation theory, this is the sum of all the diagrams where you have a particle coming in with one momentum and coming in with the opposite momentum, and you add up all the diagrams like this. It's called the propagator, and Chilene gave a non-perturbative definition, which is that the vacuum expectation value, the expectation value in the vacuum state of a peculiar kind of product called a time-ordered product, of a product of the scalar field at 2 points, which can be taken as x and 0, is defined as, well, can always be written as a Fourier integral of something, and that quantity is minus I delta prime of p times e to the I p dot x. This is the Fourier transform. This is the definition of delta prime of p. And it corresponds to what in Feynman diagrams is just the sum of all diagrams with 2 external lines. The time-ordered product is probably, well, anyone who works in quantum field theory would know, is just the product, but with phi of x put to the left of phi of 0 if the time associated with this, x0, is greater than this time, which is 0. So if x0 is greater than 0, this is phi of x, phi of 0. And if x0 is earlier than 0, then it's phi of 0, phi of x. And Chilene realized that this represented the sum of an infinite number of Feynman diagrams. And in fact, it could be used to define this without any reference to Feynman diagrams. What Chilene and then Lehmann did was to show that you could, there's a general formula for delta prime of p, which is now called the Chilene-Lehmann representation, that delta prime of p is, it has a contribution from single particle states, which is this. I'll explain the symbols in a moment. And then there's a contribution from multi-particle states, which is an integral, some function sigma mu d mu over p squared plus mu squared. In other words, the function is analytic with a, written as a function of minus m squared, it's analytic with a pole at m squared and then a cut starting somewhere beyond that. The definition of these quantities is that m is the actual physical mass of the particle, not a bare mass, but the actual physical mass. N is defined by the statement that the matrix element of phi of x between a one particle state with momentum p and the vacuum is given by, well, just by symmetry principles, you know it has to be proportional to e to the I p dot x over the square root of twice the energy. I mean, the symmetry principles like Lorentz invariance and translational variance tell you this. And the proportionality constant is defined as n over 2 pi to the 3 halves. The 2 pi to the 3 halves just comes from making Fourier integrals convenient. And so that's the definition of n, which goes here. Now, and P0 here is the physical energy. It's the square root of the momentum square plus n squared. Sigma is a sum over multi-particle states, and all you really need to know for this discussion is that sigma mu is positive everywhere. It's a sum of absolute value squares. Furthermore, well, this is just very general. It's obtained by just putting in here a sum over intermediate states and rewriting this as such a sum. That is, you use the completeness relation of quantum mechanics to get this. But then there is another step. Using the canonical commutation relations tell you that the commutator of phi dot of x with phi of 0, when x0 is 0, is equal to minus I delta cube of x minus y. And that's just the canonical commutation relations you get from the usual principles of quantum mechanics. And by applying that to this, you just take the time derivative of this and then set x0 equals 0. You can show the following sum rule, which is that 1 is equal to absolute n squared plus the integral of sigma of mu squared d mu squared. Now, this sum rule tells you immediately that n squared has to be between 0 and 1 because this is positive. Just as an aside, although this wasn't relevant to the sort of thing that Chilene was interested in, you see immediately that the maximum possible value of this integral is 1, because n squared is certainly positive or 0. The case where this integral is 1 is the case where n is 0. That's the case where the field doesn't really appear in the Lagrangian. That's the case where you're talking about a composite particle. So in a sense, a composite particle is coupled to its constituents. For example, the coupling of the deuteron to a proton and neutron is as strong as any coupling can be. Now, Chilene did, as I said, did this for quantum electrodynamics. And in quantum electrodynamics, you have the electromagnetic field here. It's a little bit more complicated because that has a vector index on it. But you get a very similar sum rule, and you see the wonders of Blackboard. That is, you get a quantity here called Z3, which is, again, it's an absolute value square of something. And here, this is a different function, but it's again a function that's positive. Z3 is what's called the renormalization constant of the electromagnetic field. And the reason it's so important is that it sets the relation between the physical charge of the electron and the bare charge of the electron. The physical charge square is Z3 times the bare charge square. And incidentally, the fact that Z3 is necessarily less than 1 tells you the physical charge is necessarily less than the bare charge, which is physically interpreted, as has been known now for 50 years or so, by the fact that if you put a bare charge in the vacuum, it tends to pull positive, that's a negative charge, but you tend to pull positrons and electrons out of the vacuum, but the positrons tend to cluster around the negative charge with the electrons being repelled, and so the bare charge is partly shielded by these virtual positrons. That's why the physical charge is less than the bare charge. Now, In lowest order perturbation theory, you can evaluate, of course, everything. And you get a formula like this. In fact, the formula says that Z3 is 1, I have to look this up, 1 minus e square over 6 pi square times logarithm of the maximum energy over which you allow in your integrals over virtual photons divided by the mass of the electron. You have to put in, and this is just the same result that was found by Waller, you have to put in a cutoff on the integrals in order to get a finite bare charge, or a finite renormalization of the charge. If you take lambda to infinity, Z3 becomes infinite. But it's worse than that. If lambda is too large, even if it's finite, this term could be bigger than this term, and Z3 can come out negative. That problem arises, as you can see, when lambda is greater than the mass of the electron times e to the 6 pi square over e square. And this number is about 200, well, actually, this whole number is the mass of the electron times 10 to the 280. That's a pretty high energy. That's more than the total mass of all the matter in the observable universe. But it's still a finite energy. And if you take the cutoff larger than that, this quantity is bigger than 1, and you've got Z3 negative, which violates its definition as an absolute value square, analogous to the absolute value of n square in the scalar field case. Now, this is perturbation theory. And the hope was that this problem would go away if you got beyond perturbation theory. And this is the sort of thing that made Chilene and Pauli interested in the Lie model, because that was a model in which you could solve things exactly without the use of perturbation theory. I should say, by the way, to avoid giving the impression that this is a purely academic problem, that, as Landau pointed out later, if you have a number of different species of charged particles, as in fact we do, and Landau called that number nu, then you get here 6 pi square over nu e square. In other words, this is 280 over nu. And if you take nu, say, to be 20, which is not a completely unreasonable number, then you get down to energies which are quite relevant. So it's really possible, with assuming more than just one charged particle, that the trouble with quantum field theory sets in at energies which are physically interesting. Chilene set to work to try to see whether or not this divergence in the limit of lambda goes to infinity is real. Now, he had this sum rule. Of course, without perturbation theory, he couldn't calculate the function sigma of mu square. But he did a clever thing. He knew that sigma of mu square gets a positive contribution from every separate intermediate state. So he could restrict his attention to simple intermediate states here and try to calculate sigma of mu square for those simple states. In fact, he took just the electron-positron state. He still had to do a lot of tricky interchanges of integrals. And in order to prove anything, he had to assume that all the renormalization constants, including the renormalization of the electron mass and field, were all finite, because otherwise he couldn't prove anything. But with those assumptions, he was able to prove that this integral does diverge. And since it diverges if you don't impose a cutoff like lambda. And since it diverges, the theory really does break down. This is his fate. Now, since he had assumed that the renormalization constants are all finite and then found that they can't be, the conclusion is that they can't be. That is, that at least one of the renormalization constants is infinite. This is a famous result that he published in 1953. Not everyone was convinced by Chilene's proof. Paul Urban in 1969 said, "Indeed, other authors are in doubt about his famous proof that at least one of the renormalization constants has to be infinite. But so far, no definite answer to this question has been found." Chilene, it should be pointed out, Chilene explicitly disclaimed having proved this with mathematical rigor. But he gave a plausible argument that it was likely to be true, and I think that's all he claimed to have done. I don't know if he ever said so in so many words, but I strongly suspect that Chilene really thought that these infinities were a symptom of a true disease of quantum electrodynamics that really did break down at very high energies, and that he wanted to be the one who would prove it. And that's why he got interested in the Lie model. So now let me go back to the Lie model. This is a model of three kinds of particles. Using the language that was fashionable at the time for cosmic ray particles, we call these a V particle, which is like a hyperon, an N particle, which is like a nucleon, and a theta particle, which is like a K-meson. And the only interaction in the theory was an interaction where a V particle can turn into an N particle and a theta particle, or vice versa. This is the only interaction. The problem, the model was set up to be non-relativistic. You ignored the recoil energy of the V and N. They were regarded as heavy. The theta was treated relativistically. Its energy was taken to be the square root of momentum square plus the mass square. But V and N were taken to be so heavy that their energy was just equal to their mass. And you never included antiparticles in the theory. And that made the theory exactly soluble. That's an old story, that theories are either soluble or, well, they can be soluble, they can be relativistic, or neither, but they can't be soluble and relativistic. You can normalize the states so that the bare V particle state is normalized, and then calculate the structure of the physical V particle state, which is the bare V particle state plus higher order corrections. The higher order corrections is an integral over states with an N and a theta. And you can adjust the overall constant here so that the V particle state, this is normalized, so I'm sorry, I didn't finish the equation, so this is +1. And you can normalize the physical V particle state by adjusting this overall constant so that its norm is 1. And then, since you can solve the problem exactly, you get a formula just like this, but now you know precisely what sigma square is. Actually, you get a formula just like the one where this was n square. And the formula reads that if you put in a cutoff, that 1 is n square plus the absolute value of g squared. G is the coupling constant associated with this vertex, over 4 pi square, just to show that the calculation is actually done. Integral from 0 to a cutoff of momentum squared d momentum over energy cubed, and where the energy is this. Well, I'm using the letter k now, so omega is square root of k squared plus m squared. And you see that if you don't put in a cutoff, this integral diverges logarithmically. But now, there's been no use of perturbation theory, and so you can't get out of this by saying, oh, the problem will go away when you include all orders of perturbation. Your perturbation theory hasn't been used at all in the Lie model, and you see that if lambda, since this diverges, when lambda is very large, this goes like log lambda. There is some value of lambda, whatever g is, there's some value of lambda at which this is bigger than 1, and therefore n squared can't be positive, but it has to be this. It's an absolute value square. So you can't get out of this using the excuse that you've used perturbation theory, because you haven't. Lee nevertheless found that some results in this model were sensible when lambda was taken to infinity. But what Chilene and Pauli showed was that, in fact, this is a theory which only makes sense when lambda is sufficiently large that this is bigger than 1. You have to introduce what's called an indefinite metric. That is, you have to violate the usual rules of quantum mechanics and take this norm to be -1. When you calculate, you find that the norm of the physical state is still +1, but you get the same sum rule, but because this norm is -1, this contribution comes from the one particle state, you get a minus sign here. And then when lambda is very large, and indeed only when lambda is very large, this makes sense, because then this more than compensates for the -n squared. So in other words, lambda can be taken to infinity only at the price of what's called an indefinite metric. Now, there had been previous discussion in the literature of the indefinite metric. Dirac had introduced it in 1942 for a reason having nothing to do with infinities. Dirac was trying to find a physical interpretation of the negative energy states of bosons. I mean, remember his famous physical interpretation of the negative energy states of positrons, of fermions, in particular of electrons, that they were all filled, and holes in that negative energy C would be recognized as antiparticles. Now, that makes sense for fermions like electrons, because the Pauli exclusion principle allows only one particle in each state. But what do you do for bosons where there is no exclusion principle? What prevents all bosons from sinking into the negative energy states? Well, the correct answer that we know today is all this nonsense about negative energy states is just nonsense. I mean, Dirac's interpretation is just wrong. The correct way of looking at antiparticles is a way that was given originally by Pauli and Weisskopf in 1934, and you find in sensible books on quantum field theory like mine. But so this use of the indefinite metric by Dirac was really trying to solve a problem that had arisen because he was looking at things the wrong way. Pauli in 1943 noticed, however, that with an indefinite metric, the sums of these integrals, the infinities in these integrals might be canceled by negative terms. And so he was ready to realize that what was going on here was the introduction of an indefinite metric. However, the indefinite metric creates problems with unitarities because it produces negative probabilities. And I think and that's what Chilene and Pauli showed, that the production of physical particles, like the physical n and theta particles, when in the sector we have n and theta colliding, you would get some negative probabilities in those collision processes. And that's why the probabilities didn't add up to 100%. It's even worse than that. Some of them were negative. I think the reason that Chilene and Pauli didn't like the indefinite metric, I mean, apart from the fact that it led to something unphysical, the programmatic reason they didn't like it is not that it didn't solve the problem of infinities. It did. It allowed the cutoff to be taken to infinity, but it solved it too easily. It solved the problem of infinities without having to really grapple with what was going on at very high energy. And in fact, experience has justified Chilene and Pauli's distrust of the indefinite metric. experience shows that it really only works when there's some symmetry principle that dictates that the negative probabilities of producing some unphysical particles are canceled by positive probabilities for producing other unphysical particles, so that the total probability of producing any unphysical particle is 0. You don't have to worry about it. This happens, for example, in one of the formalisms that's commonly used in quantizing the electromagnetic field, called the Gupta-Boiler formalism, in which the probability of producing a time-like photon produced by the time component of the electromagnetic vector potential is negative, and the probability of producing a longitudinal photon in which the polarization is along the direction of motion of the photon is positive. Both kinds of photons are unphysical, and because of gauge invariance, there's a symmetry principle that says the probabilities add up to 0. And so the total probability of producing physical photons is 100%. A similar cancellation occurs in string theory, where instead of electromagnetic gauge invariance, you have conformal invariance on the string world sheet. It produces a similar cancellation. But there's no symmetry like that in the Lie model, and as a result, you don't get this beautiful cancellation, and you really do get nonsensical results in some scattering problems. And so, as Chilene and Pauli, I think, felt, without such a symmetry as in the Lie model, the introduction of an indefinite metric leads to disaster. Now, I should say something, but at any rate, that's why Chilene and Pauli were interested in the Lie model, because it provided a way of studying the problem raised by formulas like this in a context where the formula did not depend on perturbation theory. And you could be sure that taking away the cutoff so that the integral became infinite, you would get into a logical contribution, that you would get a positive quantity given by a formula 1 minus something larger than 1. Now, I should say something about the way, where we stand today with regard to infinities. In fact, I have a lot to say about it. The correct formalism for dealing with this, I think, is the renormalization group formalism, which was presented by Gelman and Lowe about this time in 1954. When you do calculations at very high energy, at energies much larger than the electron mass, even when you calculate something that's finite, you get very large logarithms, like logarithms of energy over electron mass. As Gelman and Lowe realized, the reason you get these logarithms is you're using an inappropriate definition of the charge of the electron. You're using a definition which has to do with real electrons whose mass is me, and that's very different from the energy you're studying. The correct way to do calculations at a very, very large energy, an exponentially large energy, is to express everything in terms of what's called a running electric charge, which is defined by the values of physical matrix elements, like the vacuum polarization, at energies E. So if you define the charge of the electron in terms of the value of this kind of sum over Feynman diagrams, or you can do it non-perturbatively a la Chilene and Lehmann, then there are no large logarithms. That was really their point. At energies E, which are very large compared to the electron mass, this satisfies an equation called the renormalization group equation, which says that the logarithmic derivative of E with respect to energy is some function, but it's a function only of EE. It can't be a function of energy, because there's no, as long as you're at energies which are much larger than the mass of the electron, and there are none of these logarithmic corrections, there's simply no way that the energy can get into the equation. There's no way to divide energy by something to make it dimensionless, since the mass of the electron can't appear in the equations. This is called the renormalization group equation. And as you see, it's easy to solve. The solution is instead of given as EE in terms of E, it's given as energy in terms of charge. And the solution is that the energy is the integral from, well, actually, the energy is mu times the integral from E sub mu to E sub E, where mu is any arbitrary energy you like, anything as long as it's large compared to the mass of the electron, d little e over beta of E. That's the solution of that equation, trivially. And now you see that where the problems come from at high energy. If you, as E becomes larger, this has to increase in order, and beta is, well, beta it turns out is positive, but let's assume for a moment beta is positive. As E becomes larger, this integral has to increase, so that means this charge has to increase. But suppose that this beta goes up fast enough as a function of energy so that this integral converges when you take this to infinity. Then the energy cannot increase beyond a certain amount. The upper limit on the energy, call it E sub infinity, is mu times the integral of this to infinity. And as long as beta V increases fast enough so that this integral converges, this sets an upper limit to the energy at which physical quantities can be calculated. If Landau actually argued that, although he didn't quite use this language, what he did was equivalent to using lowest order perturbation theory for beta of E. In lowest order perturbation theory, beta of E, he didn't say it precisely this way, but it's equivalent to it, is E cubed over 12 pi squared. And then, of course, there are contributions of order E to the fifth and so on. Well, unless these contributions become more important, this growth, like E cubed, means that this integral does converge for large little e. And therefore, there is an upper limit to the energy, which is essentially this upper limit. And the mass of the electron times 10 to the 280, beyond which the theory cannot go. Landau actually, I think, overestimated the certainty of his conclusion because we really don't know that beta of E increases like this when you include all orders of perturbation theory. And so the question is still somewhat open. No one really today knows whether this integral converges or not. For example, it's possible that beta of E continues to increase, but slowly enough so that the integral diverges, in which case E sub E just goes on increasing smoothly without any problem in any particular energy. It's also possible that beta of E goes to 0 at a certain energy, at a certain charge. In other words, maybe the function beta, which increases for small e like E cubed, then turns around and does this, and goes to 0 at a certain definite value E star. In that case, the energy goes to infinity, and the charge at infinite energy is just E star. There are arguments against this, arguments by Adler, Källén, Gross, Jacqui, Baker, and Johnson. It is known in the scalar field case that, in fact, the disaster does occur. Beta of E, it's a different coupling constant, but it's a similar kind of problem. Beta does increase fast enough so that the integral converges, which means that the theory can't be carried beyond the finite energy. That's done by lattice calculations, where you don't use perturbation theory, but you approximate space-time by a finite set of points, and then you study the limit as these points become, the number of points become infinite and infinitely close together. Now, if you limit this problem to quantum electrodynamics, it's really a rather academic problem. I mean, even if you believe that the theory breaks down at a finite energy, I think one is justified in saying, who cares? since quantum electrodynamics loses its validity, we already know at a perfectly accessible energy, at energies above about 100 GeV, you don't have electromagnetism by itself, you have electroweak coupling constants. There are two of them, the SU2 and the U1 coupling constant, and electromagnetism loses its separate identity. And the question is, what happens to these individual coupling constants? And even that is somewhat academic, because when you get up to energies like 10 to the 19 GeV, gravitation surely becomes important, and nothing that you calculate just in the standard model, where you only have these couplings and the strong coupling, can be believed at energies above 10 to the 19 GeV. The kind of question of what happens just in electrodynamics or in the electroweak theory by itself is not important. And the field theory of gravity is not renormalizable in the Dyson sense. That is, the coupling constant G is something like 10 to the minus 5 GeV to the minus 2. And the fact that it has energies which is the minus 2 power of, well, has units, which is the minus 2 power of energy, means that that is not a theory that is renormalizable in the Dyson sense. So the conclusion is there probably is a problem in quantum electrodynamics, like the problem that Chilene suspected, but it is that is no longer the central question, because this has become part of a much larger picture of what happens at extremely high energies where you can't ignore gravitation. Chilene appreciated, I'm going to come back to the problem of infinities, but I want to say a little bit more about Chilene's work. Chilene appreciated the great success of quantum electrodynamics. He was not like one of these people who, when a new theory comes along, tries to say that it's not worth thinking about. He said, for example, in the 1953 Kamerlingh-Onnes conference, that there is little doubt that the mathematical framework of quantum electrodynamics contains something which corresponds closely to physical reality. He thought that the theorists of his time didn't quite have it right because of the problem of infinities, but it was certainly, quantum electrodynamics was not something you could just turn your back on. He did practical calculations in quantum electrodynamics. For example, he calculated the vacuum polarization to fourth order in E, and he calculated the radiative corrections to decay processes. He wrote a book about quantum electrodynamics, and he spared the reader his concerns about the infinities, because only at the very end of the book, in the last chapter, he got back to this point that at least one of the renormalization constants had to be infinite. His interests weren't limited to quantum electrodynamics. In 1954, he began studying the strong forces using the renormalizable meson theory that existed at that time. People knew that the pion played an important role in strong interactions, and because of the symmetries, the only renormalizable coupling you could write for a pion field to nucleons was an interaction like this, where this is called the pseudo-scalar interaction. These vectors are isotopic spin vectors, and if you don't know what it means, it doesn't matter for the purposes of this talk. The important thing is that this was a nearly unique interaction which is renormalizable in the Dyson sense, that is, where the infinities can be absorbed into a redefinition of constants, including the constant, this is a different constant from that one, including this constant in this interaction. And he set out to see whether this theory made experimental sense, and he showed that, at least in lowest order perturbation theory, it didn't, because you could calculate pion-nucleon scattering and fit the data with one value of GS. You could calculate pion photoproduction, that is, photon plus nucleon gives pion plus nucleon, and you found you needed an entirely different value of GS. So there wasn't one theory that would account for both, at least in perturbation theory. Of course, Chilene acknowledged that this result relied on lowest order perturbation theory, so it didn't conclusively kill the meson theory. Chilene, however, let the reader know about his real feelings. He said in this paper, "It would certainly be felt as a great relief by many theoretical physicists, among them the present author, if a definite argument against meson theory in its present form, or a definite mathematical consistency in it could be found. This feeling, together with wishful thinking, must not tempt us to accept this conclusive evidence, an argument that is somewhat incomplete." A creditable modesty on his part. But Chilene was right in distrust of this kind of meson theory. In fact, a decade or so later than this work of Chilene's, it was realized by the development of something called chirodynamics that low energy pions are in fact well described by a simple theory where here there's a vector gamma Dirac matrix, and here you have the gradient of the pion field. This is, plus also there are interactions, direct interactions of the isotopic spin vector of pi times the gradient of pi here. Well, complicated interactions. We have pairs of pions, interaction with nucleon, anti-nucleon pairs, and higher terms. All of these interactions are not renormalizable in the Dyson sense, and yet this theory gives a very good account of low-energy pion physics, not just pion scattering, but all sorts of things. The structure of the interactions are dictated by a certain symmetry called chiral symmetry. This theory is, every interaction in it has coupling parameters which are negative, have units which are negative powers of energy. And so the theory is not at all, doesn't fit the Dyson characterization of a renormalizable theory. But it's still true that as long as you work, it's still true that you calculate physical processes as a power series in the pion energy, which is useful then if the pion energy is small. And that to any given order in the pion energy, as long as you include every possible interaction of this sort, only a finite number of interactions contribute, and the renormalizations of those coupling parameters absorb every infinity that occurs. In other words, even non-renormalizable theories are renormalizable. The difference is that you're not calculating a power series in powers of the coupling constants, you're calculating a power series in powers of the energy. And in any given order, you need more and more coupling types. In fact, you have to include every coupling type allowed by the symmetries. But at any given order in energy, you only need a finite number of them. But you need more and more as you go to higher and higher energy. If you include interactions, a direct contact interaction between nucleon fields, then the same is true and allows you even to calculate nuclear forces. And there's a whole cottage industry now of people calculating nuclear forces using this kind of theory. This isn't an ad hoc addition. The rules tell you at any given level of energy what interactions you're allowed to include, and those rules tell you you're allowed to include this contact interaction, but not, for example, interactions with derivatives. So in a perfectly orderly way, given, as long as you stick to low energy, you can calculate anything you want. My own view is that all of the field theories that have been so far proved to be successful, quantum electrodynamics, the standard electroweak theory out of which it comes, quantum chromodynamics, together with general relativity, they're all of this type. That is, that none of them are really renormalizable in the Dyson sense. That is, none of them, all of them contain every possible interaction that's allowed by symmetry principles. But an interaction whose units are a negative power of energy has to be proportional to some mass, to some negative power. If the units are energy to the minus n, then the coupling parameter has to be some dimensionless constant divided by some mass to the power n. If these masses are very large, then you simply don't see the non-renormalizable terms when you work at energies that are much less than m. If m is something like 10 to the 19 GeV, the Planck scale at which gravity becomes a strong force, then it's natural that at the energies at which we study elementary particles, it looks like all the interactions are renormalizable in the Dyson sense. That is, their coupling parameters have dimensionless units. But in fact, all the other terms are there, waiting to become important at very high energy. And in fact, one of these terms has already been discovered. Apart from gravitation, which is discovered by the accident that gravity has the peculiar property that it adds up when you have a lot of particles, so that even though it's so weak, since the Earth has something, what is it, 10 to the 57 baryons in it, that's enough to attract things visibly. What?
It did exactly that, it attracted it.
Yeah, that's what I was doing an experiment. I'm not going to bother picking it up. That's for graduate students. But all these other terms are there, and now there's even evidence for one of these terms. The recent discovery of neutrino masses, together with the known symmetries of the Standard Model, show us that there is an interaction where you have pairs of lepton field doublets, neutrino-electron, interacting with pairs of scalar field doublets. I guess that's plus. And that this kind of interaction, you have to couple the indices together in a way that makes this invariant under all the symmetries of the theory. When the neutral scalar fields get vacuum expectation values, which is the thing that breaks the symmetries of the electroweak theory, the neutrino gets a mass. The mass you would estimate, this coupling has this thing has the dimensions of energy to the -1, and then there's some dimensionless coupling here. So the mass of the neutrino that you expect is 1 over m times the expectation value of phi 0 squared. We know what this is from the known properties of the Standard Model. The expectation value of phi 0 is 247 GeV. You don't know what there are dimensionless coupling constants here. You don't know what they are. You don't know what m is. But if you take the dimensionless couplings to be the same order of magnitude as the charge of the electron, then m turns out to be about 10 to the 16 GeV, which is perfectly plausible because there are other things going on at that energy which we know about, which I won't go into, which suggests that that's about the energy we would expect. So there is already evidence for a non-renormalizable coupling suppressed by something like a factor of 1 over 10 to the 16 GeV. The reason we don't find others is just because they're very hard to see. People are looking for proton decay, which would be an example of another such non-renormalizable in the Dyson sense, although all the infinities actually cancel. None of these theories in which the infinities all really cancel, and therefore that problem is not a serious one, at least in perturbation theory. None of these theories describe nature at very high energy, because at very high energy, at energies of the order of m, you're expanding in powers of 1, and that doesn't get you anywhere. And so we have to, in order to really make progress, we have to understand how we can take these theories and carry them to arbitrarily high energy. But from the point of view I've been describing, the famous fact that general relativity is not renormalizable in the Dyson sense is no more a fundamental problem than the fact that non-renormalizable terms are doubtless present along with the renormalizable terms, I mean renormalizable in the Dyson sense, in the standard model. They all have this problem. The challenge is to find the final underlying theory in which we can do calculations at all energies. That's the great challenge for the future. And I can see two possible ways of dealing with that. One possibility is that all of this, the gravitational field, the quarks and leptons and W particles and so on of the standard model, these are not fundamental structures, any more than the pion and nucleon are the fundamental structures of the theory of strong interactions. In the case of the modern theory of strong interactions, the fundamental structures are quarks and gluons. And the nucleons and pions are just things that appear in the effective field theory that describes hadron physics at sufficiently low energy. It's possible that the true structures in the underlying theory are something quite different, and the obvious candidate is strings. That direction, I think, is certainly worth working on. We don't know whether that's the correct direction. But there is another possibility which I wanted to bring to your attention, which is much less well known, although a number of people have been working on it over the years. And that is that our existing theories, like general relativity and the standard model, are not mere effective theories, that the physical ingredients in these theories are the ingredients of the final theory, although doubtless there'll be a lot more ingredients that will have to be added. That the true theory is a theory of gravitons and W and particles and photons and quarks and leptons and all that. It is a theory like an effective field theory, that is, every possible interaction appears in the theory, every possible interaction, possible meaning allowed by symmetry principles. At the energies at which we do experiments, most of these, the non-renormalizable ones, are almost impossible to detect. But they're all there, and but the theory does not lose its validity at very high energy. Instead, what happens is that if you study, let's say the generic coupling is G N of E, and I will divide the couplings that appear in the field equations by enough, or multiply or divide by enough powers of energy to make these couplings all dimensionless. So for example, if I'm talking about this coupling, I would multiply it by energy. So that in lowest order perturbation theory, this coupling constant increases with energy. But it's dimensionless because it has dimensions of E over M. If I look at all the dimensionless coupling constants, made dimensionless, unitless in this way, then at very high energy, they have to satisfy a renormalization group that looks like the Gelman-Low equation, but the beta function is a function of all of the couplings. And so you get a trajectory in this infinite dimensional, well, it may not be infinite, no, it is infinite dimensional, it has to be. You get a trajectory in this infinite dimensional coupling constant space. Now, it may be that as you increase the energy, these G of E's, this trajectory in coupling constant space, hits a fixed point at which the beta function is 0. There may be a point, call it G sub star, analogous to the G star I wrote over here. You see the advantages of Blackboard technologies compared to PowerPoint technology. It's still there. That there is a 0 in the beta function, and that furthermore, the coupling constants are on a trajectory which is attracted rather than repelled by this fixed point. Then, at very high energy, you just approach the fixed point, And the theory, it becomes non-perturbative if the fixed point is not near zero, but it's still a perfectly sensible theory with a finite coupling constant and no infinities. This phenomenon is called asymptotic safety. And it has been observed in a number of theories, including gravitation. There are a number of authors that have worked on this. I originated this and gave it the name asymptotic safety in 1979. And in the 30 years since then, I have not worked on this further. But other people, Reuter and Hirkachi and Ambjorn, in completely different groups, together with their collaborators, have used techniques like lattice, gauge quantization, dimensional continuation, and other techniques because you can't use perturbation theories, since this fixed point is almost certainly not at a small coupling, and shown that in simplified versions of general relativity together with some matter, that you actually do have this phenomenon of asymptotic safety. There are very general reasons to believe that the family of all the trajectories that if there is a fixed point, whether there is or not is a complicated question, but if there is a fixed point, most trajectories are repelled by it. And in fact, the surface of trajectories which are attracted to the fixed point, if you draw all the trajectories that are attracted to the fixed point, they form a surface. That surface has a finite dimensionality, even though the number of coupling constants is infinite. You're working in a surface on an infinite dimensional space, but the surface attracted to the fixed point, the so-called critical surface, is finite dimensional. There are very general arguments for that. And it's seen again and again in models. And if that's true, then even though these theories are very hard to work with because the coupling constants aren't small, they are in principle just as predictive as an ordinary theory like quantum electrodynamics, which is renormalizable in the Dyson sense. That is, they have only a finite number of free parameters, namely one less. The number of free parameters is one less than the dimensionality of the critical surface. Because, well, for example, if there's only a one-dimensional surface, meaning a single trajectory attracted to the fixed point, then there are no free parameters at all, because where you are on this just depends on the energy at which you're measuring the coupling. So instead of well, there is one free parameter, but it's an energy parameter rather than a coupling constant parameter. If this is correct, and I don't claim any great certainty that it is correct, then we are closer to a final theory than is generally thought. We'll see. Going back to Chilene, after in this work I've described, he continued his interest in general elementary particle physics beyond quantum electrodynamics. And he wrote a book on elementary particle physics published in 1964, which was very well received. Arthur Whiteman said, "That is the book on elementary particle physicists. That is the book on elementary particles that experimentalists find really helpful." His timing was unlucky. The book was written in 1964, and that was just a few years before the advent of chirodynamics and the electroweak theory put all of this in a different perspective. His death, 40 years ago, was a tragic loss, not just to his friends and family, but to all of theoretical physics. Chilene, as you know, died in an airplane accident coming back from a meeting at CERN just 40 years ago. For me, in addition to the grief that everyone else felt, I had a little bit of extra feeling of grief, because Chilene had been so kind to me in Copenhagen, and yet we had become estranged. Sometime in 1957, when I was just finishing my graduate work at Princeton, Chilene visited Princeton I didn't see him, but he left a note in my mailbox. Apparently, he had seen a draft of my PhD thesis. My PhD thesis was another unimportant piece of work. It was about the use of renormalization theory in perturbation theory to deal with strong interaction effects in weak decay processes. Since we didn't know the theory of weak or strong interactions, there really wasn't much one could do with this. But his note seemed angry, not just dismissive. Dismissive, I would have thought, would be a reasonable reaction. But his note seemed angry, and it said that my work showed all the misconceptions about quantum field theory that were then common among theoretical physicists. And my thesis was no great accomplishment. I was just in a hurry to get out of Princeton. But I didn't see why Chilene was so angry about it. He may have been annoyed because I followed the common practice, which was common at the time, just of not worrying about the fact that the renormalization constants were infinite. As long as I could manipulate them and get a finite answer, I didn't care whether I was manipulating infinite quantities. But everyone was doing that. So I mean, that may have been why he was angry, but I didn't really, it seemed odd to me. Torsten Gustafsson, whose nephew was in the audience, said of Chilene in 1970 that, like Pauli, remember who was his collaborator, like Pauli, he often expressed his opinion in a provocative fashion, especially to well-known physicists. I certainly was not a well-known physicist, but I was just getting my PhD. But maybe Chilene was actually paying me a compliment by treating me like one. I didn't see Chilene again after this, and which I very much regret, I never replied to his note. And I regret that because I think if I had replied, we could have understood each other and been friends again. And of course now that's not possible. But I feel in talking to this audience, in a way I've been talking to Chilene and making up for my failure over 50 years ago to get back in touch with him. So in a sense I am in touch with him now. And I'm awfully grateful to Cecilia Jarlskog and the other members of her committee for giving me this opportunity to pay my respects again to a man to whom I owe so much. Thank you. Gone way over time, and I know everything I said was crystal clear, but even so, I'm happy to entertain questions.
My question.
Yeah, I know. So, are there any questions? Yes. I'm going to show him. Yes? No, you were just scratching your nose. I really wish someone would ask me a question.
You didn't say, anything about, the abelian, non-abelian theory.
Yeah.
The sort of things we were discussing, they were all, let's say,
Right.
fashion stuff.
Yeah, well, in the abelian theory, the beta function goes like EQ, and in the non-abelian theory, it also goes like EQ, but it goes like minus EQ, and that's provided that the number of gauge bosons is sufficiently large compared to the number of fermions on which it acts. And that means that when you go to high energy, because beta is negative, the coupling constant decreases, and so it approaches zero. So at very high energy, quantum thermodynamics is not only a renormalizable theory, but this running coupling constant becomes very small, and you can use ordinary perturbation theory. There are lots of complications in that. This was the great discovery of Gross and Wilczek and Politzer, that the sign changes in non-abelian theories. Now, from my point of view, quantum chromodynamics is just a particularly simple example of an asymptotically safe theory where the coupling constant happens to, G star happens to be 0. So that as you go to high energy, you approach it. But we can do calculations because when you're at very high energy, you're close to 0 coupling. The kind of asymptotic, and you could say that the space of all possible couplings you might add to quantum chromodynamics, which are still consistent with the principle of gauge invariance, which includes all kinds of non-renormalizable couplings, that space is infinite dimensional. But the critical surface, which is attracted to the fixed point at 0, is finite dimensional. It's just a one-dimensional trajectory. The difference is here, the fixed point is not at 0, and so calculations are much more difficult. In fact, one of the arguments for my statement that the critical surface, I was hoping someone would raise a hand and say, what's the argument for the fact that the critical surface is finite dimensional? One of the arguments is based on dimensional continuation. You can, in addition to varying constants, you can actually vary the number of dimensions in which the theory is written. Now, there are some dimensions in which, namely 2, in which general relativity becomes an ordinary renormalizable theory with a fixed point at 0. As you increase the number of dimensions of space-time from 2 to 4, the fixed point moves away from, now that's a case in which the dimensionality of the critical surface is certainly finite. Because the fixed point is at 0, we can calculate what you need. In 2 dimensions, the simple Einstein theory is renormalizable, but all the complicated things you might add to it are not. You can, as you increase the dimensionality, the fixed point moves away from 0. And as it moves away from 0, the number of dimensions in the critical surface can change. And this is what typically happens in models. It can change from 1 to 2 and so on. But it's hard to believe as the dimensionality goes from 2 to 4, it changes by an infinite amount. And so you expect it still to be finite. There are other arguments that say the critical surface has finite dimensional, but I'll spare you them. Well, now Cecilia has broken the ice. Any other questions? Okay, well, it's very late, so thank you.
Var är de där handdukarna